Good morning, students. Last class we discussed about the theory part of all five modules in metal forming. Today I am going to discuss regarding the problematic part in module 1. Module 1, the problems which related to what are the problems you will get is the problems which related to engineering stress you will get, engineering strain you will get, true stress you will get, true strain you will get, reduction of the material you will get, maximum principal stress, maximum principal strain, uh, shear stress, flow stress, metal flow stress, Tresca maximum shear stress criteria, one ms distortion energy criteria, engineering stress, everything, and ductility in terms of percentage you will get. Okay, you just see this. These are all the formulas, important formulas. These are the formulas are very important to solve the problems. Okay, first I was concentrated on the first 10 problems. Okay, I'll just explain what are the things are given and what you need to find out. You just solve this 10 problems, first 10 problems. Remaining problems I'll continue in the next class. First of all, you just see the formulas. So many formulas are there here. Formulas, first one, stress x, stress y, tau of xy. Correct. First is the stress in x direction, y direction, shear stress, longitudinal stress, shear stress. Tau is mentioned as shear stress. Okay. Stress in x and y direction you can find, and shear stress you can find. Okay. This tan theta is, 2 theta is there now. That is for um, principal stress. Okay, you need to find out the principal stress. For that, you need to find out tan 2 theta. Okay, maximum principal stress is stress max, stress 1. Some problems they will going to ask only engineering stress, engineering strain. Okay, some problems they will going to ask maximum stress and maximum strain, principal stress and principal strain. In that cases, you will get you need to use maximum principal stress formula and minimum principal stress formula. Okay, next, uh, flow stress. See here, flow stress or yield stress we can say. Okay, you flow stress also they'll going to ask. Okay, these are all the varieties. Okay, mean flow stress, Tresca. This is maximum shear stress theory. Okay, Tresca yield criteria and voluminous yield criteria is almost of all the shear stress criteria only. Okay, based on these two formulas, how the shear will take place, that they'll going to explain. Okay, each having different formulas. Okay, Tresca or maximum shear stress criteria, it will take tau max is equal to stress 1 minus stress 3 by 2. Stress 1 is upper layer and stress 3 is the up lower. Okay, in three directions, stress 1 in x direction, stress 3 in z direction, like that it is. Okay, one image or distortion energy shear stress criteria also you're going to use. Engineering stress, you know this and all, these are all most common formulas you already used in material testing lab also. Engineering stress, engineering strain. Okay, but most of the classes in companies and all we're going to use true stress. Okay, and ductility, Ductility means how much, how the material is soft, how uh, the that is nothing but softness of the material we need to see. Okay, because in metal forming process, if the material does not have any ductility, the metal will not undergo the shape. Okay, we need to convert it. Okay, it will undergo some cracks or some cold shrinkages. It will take place if the ductility is less. Okay, if the ductility is more also, it's waste only. The strength of the material gets reduced. Okay, that is the main thing you need to see this 13 problems, 13 formulas you need to uh, practice it properly. Okay, and the first problem. Okay, let us see the first problem now. First problem is determine the engineering stress. Here only first problem which concentrate on basic things. Okay, determine the engineering strain, true strain, reduction. Engineering strain means if you are going to apply a force, the material will offer some resistance against that force, that is strain. Okay, you need to find engineering strain, total strain also you need to find, and true strain. Strain with instant applying load, that means every increment of load you need to find out true strain. Okay, and reduction, if the load is applied, see for example tensile force is applied to it, means the metal gets definitely reduction in its volume, and it will increases in its length. Okay, a bar which is doubled in length, that means elongation is doubled with its length. For example, 100 length is there initially. 100 length bar, if you are going to apply a force, means it becomes 300. Okay, double to the length of it. Okay, like that, the first thing is. Second is bar is off in its length, that means 100 material, if you are going to apply a load, means it will elongate it up to 150 Okay, this is the first problem. Okay, same thing you need to use. See, engineering strain formula you need to use. Engineering strain, true strain formula you need to use. See, engineering strain, different formula. Change in length by original length. Here true strain is logarithmic of 1 plus engineering strain. Okay, this is the actual thing. This derivation you already seen. It is there in previous this one. What I have given the this document. No, in that it is there, you just go and see. Reduction in its cross section area, of course. If the load is applied, tensile force is applied, means reduction in the material takes place. This is original length, means final original area, initial area, final area divided by final area, you will get the change in its length. Okay, that means reductions of area takes place, correct, reduction in its area. Okay, that is the thing. Okay, this is for with respect to 4 bar of double in its length. Second is half of its length. Okay, this problem is very easy, you need to solve it. Okay, if you have any doubts you can ask me, okay, later. Second problem is you need to they ask you to find out true fracture stress and fracture strain. Okay, true fracture stress and fracture strain, that means here fracture will comes. The test specimen with 12 initial diameter and 50 gauge length. You know that gauge length. Okay, gauge length is nothing but the area. If your specimen is prepared for tensile test, means the center part. Okay, it will come uniform cross sections from the center. It is taken as gauge length. After that, the metal will gets expanded. Metal will gets increase in its area because of for gripping length. Okay, the maximum diameter at the fracture is 10 Initially, the tensile specimen before testing is 12 After that, when it will become fracture, no, that time it will reduce to 10 that one it will reduce to 10 Okay, find the engineering stress and a maximum at maximum load. Engineering stress at maximum load you need to find out. Okay, and true fracture stress you need to find out. Second one is true strain and engineering strain you need to find it. Simple. Here also four thing you need to find out. Engineering stress, engineering strain, and true strain you need to find out. Okay. Here you see initial diameter, initial area, maximum load applied during fracture load. Okay. Uh, Fracture load, maximum load means before fracture it is taking the load. After this fracture load. Okay, these are all the things are there. Okay, second problem is also easy. There is no there is nothing difficult in this. Okay, next is third problem is also related to engineering stress, strain, true stress, true strain, same thing. Okay, You just see the low carbon steel is subjected to a tensile load of 7,000 kg, assuming no volume change during extension. Determine the engineering strain, true stress, true strain. The initial diameter of the rod is 13 mm and the specimen under the load is 12 mm. That means initially it is 13 mm, the specimen under the load is 12 mm. Okay, 1 mm reduction in area. Okay, same thing, load 7,000 kgs means you need to convert into Newton into 9.81, you will get the Newton. Initial diameter is 13 and the final diameter is 12. Okay, engineering stress you need to find out, load divided by original cross section area. That means 68.67 divided by 13. You will get a 13, you convert it into area. For converting of a bar, area is pi by 4 d square. Okay, you need to you'll get the engineering stress. Okay, 517 MPa. True stress means load divided by instantaneous change in length, that is 12 mm you will get. Okay, after loading the metal, the diameter will gets reduced to 13 to 12. Okay, the 12 mm only you need to take. Next is stress you will get. Next, find engineering strain. Engineering strain means same formula you need to use. True strain means same formula. Okay, same thing, nothing changes is there in this third problem also. Okay, fourth problem. Okay, the fourth problem is ductility in terms of percentage reduction in area. Okay, here the ductility in terms comes. Okay, ductility means you're going to measure the ductility of the material based on the reduction in area, based on the changing in, for example, okay, if the load is applied to a tensile bar, okay, 100 bar, if the load is applied, 50 kilonewton load is applied means it will becomes to 150, with reduction in its cross section, that the 50 will tell that ductility only, because brittle material will get less extension of material. For example, the load is applied to the better material, the elongations of the material will not take place, suddenly it will breaks. Okay, but in ductile material, cup and cone shape will form. Okay, if the cup and cone shape will form means it will increases the length will be gets increased, but the area will gets reduced. Okay, see here also the ductility you need to find out in terms of percentage in reduction. First formula you are going to use ductility formula in the problem 4, that is to find the ductility in terms of percentage reduction in area. That means we know that percentage decrease in area is decrease in area divided by original area. Okay, original area is how much you need to find. Original area 12.5. 12.5 is diameter, you need to convert pi by 4 into 12.5 5 whole square, that you will get is how much you will get. Area 12.5 square minus 10.5 square into 100. Okay, area only he has given. Okay, specimen steel having original diameter of 12 mm tensile load. Okay, here you convert into area also same thing only will come. Okay, same thing only it will come. Okay, if you are convert also same thing, because here yeah, he is mentioning in percentage. Okay, if you convert it in area also, here he has not converted, because 12.5 mm directly has taken, direct diameter he has taken, and he has mentioned in as a naught, but it is wrong. Actually you need to convert. Area means pi by 4 d square minus pi by 4 d square only you need to do. Pi by 4 d square, only thing is here 12.5 you need to a naught, where the a naught is there you need to mention 12.5, where af is there you need to mention 10.5. Okay, you'll get 29.44. That means percentage of reduction area is 12.54. 44 means 29% of ductility of in the material is there. Okay, next is true strain at fracture. Fracture you need to find out. Okay, true strain at fracture you need to find out. Load at a fracture, instantaneous circle suction area and other thing. Okay, next is engineering stress at fracture. Okay, this is true stress at fracture, this is engineering stress at fracture. Okay, stress F is equal to pf by a naught. Pf by a naught, a naught you know, see here you need to find out like this. Okay, pf is 450, stress F, that is here is there as mentioned 450 into area. True stress means pf by area, this is area, the thing is like this. Okay, to find this one, say stress fracture. Okay, you can do this, not a problem, not an issue. Only thing is when area, okay, load is same for both. Only thing is diameter will changes. Okay, initial thing is for engineering stress, you need to find out, you need to put 12.5 mm. Fracture, you need to put 10.5 mm. Okay, this is the thing. Okay, again fifth problem is also same. Fifth problem is also, it's related to, fifth problem is also related to screw stress for fracture only. Okay, same thing. Okay, you can solve in this also, same thing is there. Okay, next, sixth problem. Okay, see here in this problem he has given in matrix form. Okay, three-dimensional state of stress you need to find out here. Three-dimensional state of stress means, of course, principal stress you will get. Okay, the stress which is acting, the volumetric change. For example, the load is applied to the material means volumetric of change of material will take place. That means change in volume will take place if the load is applied to the material. Okay, that you need to find out with the help of principal stress and maximum shear stress. Okay, this principal stress, if the problem will comes like this metric form, you need to see that it is in the form of matrix. It is in the form of matrix. Okay, please go through this. Okay, here you need to convert. See, he has told that determine the principal stress and maximum shear stress. Okay, principal stress and maximum shear stress. For principal stress, you need to find out, means you need to convert that into this form. Okay, you need to convert this is the formula for that: stress x minus stress tau of yx tau of zx. Tau of xy, stress y. That means stress in x direction, strain will take place in other two directions. Same thing. Stress in y direction means strain will take place in other two directions, xy directions and zy directions. And stress in z direction means strain will take place on other two things. Okay, see, on the comparison we will give the stress matrix. We will give stress x is 80 mm, 80 MPa this year, 80 MPa. Okay, 80 MPa. Stress y is minus 40 MPa, minus 40. See, stress y is minus 40 MPa. You need to see in diagonal form, 80 minus 40, 60. Next is 60. See, stress z is 60 MPa. Next to tau of xy. See, here tau of xy and tau of yx, same thing. Okay, you'll get 20 MPa. This and this is same. 20 and 20 is same. Minus 50 and minus 50 is same. 30 and 30 is same. Okay, you need to find out with the help of the principal stress formula. You need to find out stress x, stress in x direction, y direction and z direction. That means stress 1, stress 2, stress 3 you need to find out with the help of that formula. And maximum shear stress you need to find out. Tau max is equal to 89 MPa. That means stress 1 minus stress 3 by 2. Stress 2 will not considered in this maximum shear stress. Okay, you will get, okay, stress 1 minus stress 3. Okay, same thing in the seventh problem also, same thing is there. Principal stress only you need to find out. And here one doubt you will get, that means simultaneously see here, stress 3 minus 10 minus 100, stress 2 minus 4600, stress plus 248 in 10 to the 3 is equal to 0. That means simultaneous equation. With the help of that only you need to find out stress 1, stress 2 and stress 3. Okay, next, seventh problem is also same almost. Eighth problem is also same, principal stress only. Ninth problem also same. Ninth problem means some seventh problem is also same and eighth problem is also same. Ninth problem only changes, you need to find out here maximum magnitude and direction of principal stresses. Okay, magnitude, see, the magnitude and directions of principal stresses. Okay, maximum magnitude means maximum principal stress. Stress max is stress 1 you need to find out. Maximum principal stress for formula is this one: stress x plus stress y by 2 plus square root of stress x minus stress y by 2 tau of shear stress xy whole square. Okay, minimum is only changes, subtraction you will get. Okay, stress x plus c, same for maximum, same thing. Minimum, same, only thing is minus you will get here. Okay, and another one is directions of principal stresses. Okay, to determine the directions of principal stresses. Principal stresses means directions only you will get. Okay, in what way, in which direction the material will get fails. Okay, usually the material will get fails at 45 degree. Okay, that will tells in Tresca and Vanimir yield criteria. Okay, Tresca, both Tresca and Vanimir yield criteria will tell us that the material will take place, the breaking or failure of material will take place at 45 degree. Okay, you need to concentrate, you need to solve till 10 problems. Okay, if you have any doubts, you can send a message in WhatsApp to my number, okay, or in Google Classroom, okay. We will discuss, okay.